one of these methods, so after clip and align, is LiT. So logged image training. Okay, logged image to text tuning essentially. So this is very simple. So let me get the notation right. Capital L would mean, so this is again tall text encoder, tall vision encoder. This is clip setting of info NC. All of those things are same. All I am doing here is looking at how I am training my text and vision encoders. Yeah. So L mean I am initializing from pre-trained model. In case of image, if it is in this case, I am pre-training initializing for pre-trained image model, and I am locking it. I am not going to fine-tune it or update it, the parameters of my vision encoder. Yeah. U small mean that I am going to initialize them randomly. So in this case, the text encoder is initialized randomly, and I am going to train it. Yeah, simple. Capital U mean that I am going to initialize from the pre-trained weight, but I am going to train it as well, and that's it. These are all three symbols. Yeah. So this setting U and U mean that I am going to train the image network. I am going to train the vision text network in the info NC way. So this would be corresponding to what? Clip and align. Yeah. So this training strategy. This paper is all about training strategy. So, and this is in CVPR 2021. So this is essentially clip. And this is a special variant where you have pre-trained the image encoder, and you are not going to update that. You are only going to update the text. The purpose, the job which clip and align is essentially doing is very simple. So basically what they are doing is they are trying to align the modalities, as you can see. Yeah. So they are trying to bring the image and text into same feature dimensional space. Yeah. And you can do that in multiple ways. You can do that by training both image and text, or you can do that by training any one of them. Yeah. Okay. So it would have been interesting to see that another experiment where they would have initialized the text model and locked it and trained the image from scratch. Yeah. So they didn't do that. We did that as part of CLMIU, and the answer is don't do it. Okay. So I will tell you why. So this is clip, and this is fine-tuned from scratch, and this is locked image training. So this first setting is where you locked the image and just train tune the text model is the best thing, and it outperforms with quite significant margin. Yeah, just that. So when we were discussing CLMIU, so you have the transformer encoder. Yeah, you can choose to initialize that transformer encoder, multimodal transformer encoder in CLMIU as starting from BERT or as starting from vision, yeah, from SIT. Yeah. So when we start it from BERT, the performance of the same system for let's say conceptual captioning, so for CIDR score for captioning task was around 60, 70. And when we initialize same thing from image and train the CLMIU model, the performance was around 130. So almost twice. Yeah. So perhaps that's why they didn't do it. Yeah, but it would have been interesting to see, because this is different setting. Yeah, that is different setting. That's generative task, that a unified network. You have a shared network between vision and language in CLMIU. Here you have separate networks for vision and language. But it would have been interesting to see that too. Okay, and the results are consistently better. You can see that it is outperforming on zero-shot transfer accuracy on ImageNet and a bunch of other data sets with decent margin. Yeah, for object and for classification both. Let's move on to the next step. So lock image training was quite decent, but there is a lot of stuff which you can do, yeah, and that's what people are trying to do here. Yeah. So this is the standard setting. You have images, you have image encoder, you get image representation, you have text encoder, text representation, and then you do info NC. Simple. Yeah, that's clip. But you can do a bunch of other stuff as well. You have images. You can choose to take multiple view of the images and do contrastive learning on images as well. Yeah, that's a sensible thing to do as well. CLMIU has already established that doing self-supervised learning of vision modality along with the multimodality is helping. And that is exactly what is happening here as well. So you take the view 1 and view 2 of your sample. So you have view 1 and view 2. So you take that and then you do simply info and CE here. You can take the text augmentation as well. So you can modify the text a little bit. Cute white cat, instead of cute white cat, you can write cute white kitty. And you can think of more fancy way to augment this. And you can do that augmentation as well. And then you can do the self-supervised learning cross-modality between the text and image. Yeah, you can do within text self-supervised learning as well. So these green things are basically self-supervised within modality. And this on the diagonal here, you have between modality. So, okay, so I should use maybe another color. So this is between modalities. Okay, maybe black. Okay, so this is between modality. And the other stuff is within modality. Yeah. So where the green arrows are depicted here, for example, this is between image and image, this is between text, and so on and so forth. So idea is that you do contrastive learning within images, you do contrastive learning between images and text on the black highlighted part, which is 0, 2, and 3 in the relevant position. So it is this one, and this one. Yeah. And then there is another thing which they did is that they took the text part only and they look in the database of few million images and they find the nearest neighbor with respect to text. So you have text representation, you have text vector, you do the text search and find the most similar text. You take the image corresponding to that most similar text which you retrieve corresponding to your nearest neighbor, and you do that and you use that as positive label as well. Yeah. And do again info and CE. Yeah. So this DeCLIP, by using this self-supervised learning within modality and multi-model cross entropy or multi-model info and CE, works very well. So the one of the good advantages is that instead of using 400 million images, they are able to get better results than CLIP using 60 million images. Yeah, and CLMIU also showed this, that you can use only 2 million images and can get similar results at 1.8 billion images, so 250 times less data. So here they are showing that you can do that using, I don't know, 6 times less data, 7 times less data. So while we have seen that if you do self-supervised learning properly, you can use 200 times less data as well. Good. In parallel to DeCLIP, people in SLIP started to use similar things. So they have language supervision, they have self-supervision, and they have cross-model supervision as well. So it is very similar to DeCLIP, so I will not go into detail of that. I am giving it as a reference just to see. Yeah. So there are people who started to do things in parallel. So there is multimodality going on, and there is self-supervised learning within modality, and it also brings similar improvement. You can see. Yeah. So SLIP is also quite significantly better. Okay. This is the last work in the case of the vision language pre-training using contrastive learning. Yeah. So we have already covered DeCLIP, where you are doing self-supervised learning. Now we will look at UniCL. Okay. So the idea is very simple here as well. So when you are doing supervised learning, in case of ImageNet, what you have image and you have text corresponding to that, and that text is your label. Yeah. It's one index, but there is text. Yeah. Nevertheless. Okay. So that setting which you have in the case of image label is this page here, this blue space. Yeah. So let me make it bigger. Yeah. So that is clear. So this plane, blue plane, represents the supervised learning. When you have rich pair data in terms of 400 million vision language pair, then you get something which is in this green pair. So you have image and you have corresponding rich text associated with it. Could be noisy, could be clean, doesn't matter, but that's the setting. And the method you use here is cross entropy subcon. We didn't study subcon, but it's very straightforward paper. So, and the method which we study here is clip and align. Okay, so what they wanted to do is combine both of them. So They want to use the supervision from a single label, and they want to use the supervision from the rich text as well. Okay, so idea is simple, yeah. And actually, if you think about it, it's very straightforward. So, for example, so this is the image label space. So you have images of the husky dog, and these represent those corresponding images. Yeah. So you can design the prompt as you were designing the prompt to do inference, zero-shot inference. Yeah. So you can say a picture of husky, a Siberian husky, an image of husky, yeah, something like that. Yeah. So that gives you the text, and you can have the normal text which is coming from your normal image to text pair, which is having more detail provided by human, and you just combine that. Yeah. So now you can do learning using the label data like ImageNet, which we know is quite clean. It's not fully clean, but it is quite a bit more clean than the 4 million data which you have downloaded from internet randomly. Yeah? So it's significantly more clean. And here you have noisy data. Okay, good. And that is it. Yeah. So that is your UniCL method. So they showed that if you do that, you get quite decent performance for zero-shot learning and so on and so forth. Yeah. So what you want to do now is quite interesting. So we have focused so far on vision and language only. Yeah. So CLIP, Align, LiT, you name it. Yeah. DeCLIP. All of them are focusing on image, and UniCL. All of them are focusing on this image. And so there is this very interesting work, ImageBind, which is making this central assumption that so this is the text and this is the image. And so far we have looked at this combination, and that's what is there in Align and CLIP and so on and so forth. So what these people investigated is that image is also related to depth image. Image is also related to thermal infrared images, and image is also related to video, and videos are also related to audio and IMU data. Okay. So you have paired modalities everywhere. It's not just image and text. Yeah. So you have image and depth as well. You have image and infrared as well. You have image and heat sensor data as well. Yeah. So basically you have alignment everywhere. So the solid line here are showing the alignment which is directly present in the data. Yeah. So what they did is that they took the CLIP encoder, vision and language. They froze vision and language encoder of the CLIP. Yeah. So LiT was out already by that time. Yeah. And then they took the depth and they train it with depth. Image is frozen, locked. Text is frozen, locked. You bring in the new modality depth. So you fine-tune that modality. You bring thermal, you fine-tune that. You bring audio, you fine-tune that. Simple, yeah? And the loss you use is info NC. Same loss. Nothing is changed. Yeah? Same as LiT. The part which is pre-trained, fix it. What is the purpose here? You want to have the alignment between depth and image as well. So you want to bring the depth in the same space where your vision and language space is, because vision and language space is already aligned. Yeah. So you want to align now the depth in the same space, audio in the same space, thermal in the same space, inertia, IMU data in the same space as well. And that is it. And that enables them to do quite interesting stuff. Yeah. You see that this way they started to find that there are links even between the modalities which are not directly related, which are not directly paired. So there will be now alignment between audio and text. Yeah, there will be alignment between audio and temperature data, for example. Yeah, thermal imaging data, and that is exactly what they are going to show here. Good. So they use cross-model retrieval. So they use the sound of fire, and they retrieve the image, and surely you get the images corresponding to sound of fire. Yeah, good. And they use baby sound, and they retrieve that, and they retrieve the depth image corresponding to the audio. So you see, audio and depth are not paired. So if you go up here, you see that audio and depth are not directly paired. So this is the depth image. Audio and direct does not have, the network hasn't seen them. But since audio is in the same space, depth is in the same space, you can do that. Yeah? So they have retrieved the depth corresponding to fire. So sound of fire, you can see these are just fireplaces, yeah, and so on and so forth. So that enables quite a lot of applications. So they evaluated it on zero-shot performances and so on and so forth on different tasks, on ImageNet and on other, because they are using audio, they are using thermal data and so on and so forth. So they evaluated it on multiple scenario, and they are performing very decently. So the absolute state of the art is here, yeah. So that is the absolute state of the art for specific network design for that specific task. So they are not outperforming that, but they are not doing bad either, yeah. So that is the main message behind this ImageBind.